You see that bright speck racing toward the sun at 245,000 kilometers per hour? That is not supposed to exist. July 1st, 2025, Chile's Atlas telescope picks up something moving wrong. Too fast. Wrong direction. By July 2nd, astronomers know the truth. This object came from outside our solar system, the third visitor we have ever detected, and some very serious scientists are asking a question nobody wants to hear. What if this is not natural? Meet 3 Atlas, 8 billion years old, possibly older than entire galaxies, coming in hot from the direction of Sagittarius, straight from the galactic center where our Milky Way keeps its deepest secrets. When it was spotted, it was already 420 million miles away, screaming inbound at speeds that break every record. The fastest visitor our solar system has ever recorded. If you value documented space discoveries like this, subscribe. It is the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA Science Archives published July 3rd, 2025, and the Astrophysical Journal Letters published August 20th, 2025. Deep technical papers that reveal what mainstream media missed. Now back to the information. Here is what makes 3I Atlas different. Every natural comet we have studied, Halley, Hale-Bopp, all of them, formed with our solar system 4.6 billion years ago. 3. I Atlas predates that by over 3 billion years. University of Oxford astronomer Matthew Hopkins ran the numbers. 68% confidence interval puts 3 I Atlas between 7.6 and 14 billion years old. If the upper estimate holds, this object witnessed the birth of our galaxy. The trajectory tells a story astronomers did not expect. 3. I Atlas came from the thick disk, the ancient stellar graveyard where the oldest stars in our galaxy slowly die. Its vertical velocity through galactic space measures 18.5 kilometers per second. That is high. Higher than nearby stars, higher than normal interstellar objects. This thing has been bouncing around the Milky Way for eons, picking up gravitational kicks from dead stars and dark matter streams we barely understand. Rio Hurtado, Chile, July 1st. The Atlas Survey Telescope locks onto a magnitude 18 smudge moving through Serpens and Sagittarius constellations. Observatory code W68 records the discovery at 0647 Universal Time, 3.5 astronomical units from Earth, 4.51 astronomical units from the Sun. Already moving at 61 kilometers per second, but the real shock comes 12 hours later. Follow-up observations from Deep Random Survey, Lowell Discovery Telescope, and Canada, France-Hawaii Telescope all confirm the same impossible thing. This object has a coma, a fuzzy atmosphere of gas and dust. It is outgassing. Comets do that when solar radiation heats their icy surfaces. Except 3. I Atlas was already doing this 6.4 astronomical units from the Sun, twice as far out as Jupiter. That should not happen with water ice. James Webb Space Telescope turns its instruments on 3. I Atlas, August 6th. Near-infrared spectrograph reveals something that makes astronomers pause their coffee. Carbon dioxide. Lots of it. An 8-to-1 ratio of carbon dioxide to water ice. That is off the charts. Most comets are mostly water. 3. I Atlas is mostly carbon dioxide ice. Dry ice. The stuff that sublimates at minus 109 degrees Fahrenheit. NASA Hubble. Observations from July 21st narrow down the size estimates. Original calculations suggested 20 kilometers diameter. Vera Rubin Observatory data dropped that to 10 kilometers. Hubble gets it down to 3.5 kilometers maximum, possibly as small as 440 meters. Either way, this is the largest interstellar object ever confirmed. And it is moving through our solar system like it owns the place. The orbital mechanics raise eyebrows in ways that keep planetarium directors awake at night. Eccentricity of 6.141. That means 3. I Atlas follows an extremely hyperbolic path, essentially a straight line that barely curves around our Sun. It will reach perihelion October 30th at 1.36 astronomical units, just inside Mars' orbit. Then it rockets away forever, never to return. Here is where Harvard astrophysicist Avi Loeb enters the story. July 21st, Loeb and collaborators Adam Hibbard and Adam Crowell publish a paper titled, "Is the Interstellar Object 3I Atlas Alien Technology?" They run the probabilities. The trajectory that brings 3I Atlas close to Venus, Mars, and Jupiter has a likelihood of less than 0.005% for a random natural object. Loeb notes the timing. 3. I Atlas entered the outer solar system boundaries roughly 8,000 years ago. That coincides almost exactly with when human civilizations developed advanced enough technology to start documenting history. Mesopotamian cities, Egyptian dynasties, Chinese astronomy. The question hangs in academic air: coincidence or reconnaissance? The alien spacecraft hypothesis focuses on specific observational details. 3. I-Atlas will be hidden behind the Sun from Earth's perspective during its closest approach in late October. Perfect timing for a spacecraft to conduct what Loeb calls a clandestine reverse solar Oberth maneuver, using the Sun's gravity to brake and potentially redirect toward Earth or another planet. October 3rd. European Space Agency, Mars Express, and ExoMars Trace Gas Orbiter prepare to observe 3. I-Atlas from 30 million kilometers away as it passes Mars. High-resolution stereo camera and color and stereo surface imaging system will attempt to resolve the object's shape. Is it elongated like a spacecraft? Spherical like a natural comet? These observations could settle questions or raise new ones, but the scientific consensus pushes back hard. University of Oxford astronomer Chris Lintott calls the alien hypothesis nonsense on stilts and an insult to the exciting work going on to understand this object. UCLA astronomer David Jewett, who leads Hubble observations, points out the fundamental problem. No one knows where the comet came from. It is like glimpsing a rifle bullet for 1,000th of a second. You cannot project that back with any accuracy to figure out where it started on its path. The chemistry tells a more complex story. Gemini South telescope observations from August 27th reveal cyanide in the coma, exactly what astronomers expect from heating comets, but also nickel and iron, metals that should not exist in normal cometary outgassing. University of Edinburgh astronomer Cyrielle Opitom suggests these metals might be trapped in carbonyl compounds that explode into gas under solar heating. 3. I-Atlas grows a tail, 35,000 miles long by late August. The Hubble image from July 21st shows a teardrop-shaped cocoon of dust streaming away from the nucleus, normal cometary behavior, yet the carbon dioxide to water ratio remains unexplained. Catholic University astrochemist Martin Cordner admits there is still a lot we do not know. If you value documented space research like this, subscribe. Your support enables deeper investigations into discoveries that challenge what we think we know about our galaxy. The size estimates keep shifting as better data arrives. Early Atlas observations suggested something massive. Vera Rubin Observatory brought it down. Hubble refined it further. The upper limit sits at 5.6 kilometers diameter. The lower limit might be as small as 320 meters. That range matters because larger objects are exponentially rarer in interstellar space. Finding a 20-kilometer visitor would be winning the cosmic lottery. Finding a 3-kilometer visitor is merely improbable. Speed builds the mystery deeper. 1I Oumuamua clocked in at 26 kilometers per second. 2I Borisov measured 32 kilometers per second. 3I Atlas screams through space at 68 kilometers per second at perihelion. The fastest natural object ever recorded in our solar system. That velocity comes from billions of years drifting through gravitational fields of dying stars, picking up momentum from encounters we can only model, not observe. September, observations from multiple ground-based telescopes tracked the growing activity. The coma expands from 13,000 kilometers diameter in June to over 26,000 kilometers by July, twice Earth's diameter. Spectroscopic analysis confirms water vapor, carbon monoxide, and carbonyl sulfide outgassing alongside the dominant carbon dioxide. International Gemini Observatory captures the comet glowing green during September's lunar eclipse, suggesting diatomic carbon emission lines. University of Michigan doctoral student Astor Taylor, part of the original discovery team, frames the scientific significance. 3. I-Atlas likely contains ices, especially below the surface, and those ices may start to activate as it nears the Sun, but until we detect specific gas emissions, we cannot say for sure what kinds of ice or how much there is. Every spectral line provides clues about conditions in the stellar nursery where this object formed billions of years ago. The galactic origin story emerges through careful orbital mechanics. University of A Coruña researcher Xavier Perez Couto traces 3. I-Atlas backwards through 10 million years of gravitational encounters. The object passed within 1 parsec, 3.3 light years, of 25 known stars during its journey to our solar system. Each encounter altered its trajectory slightly, erasing direct evidence of its birth system. 3. I-Atlas belongs to the galactic thick disk population. These are ancient stars with low metallicity, fewer heavy elements than our Sun. If 3 I-Atlas formed around such a star, its chemistry should reflect that primordial composition. The high carbon dioxide content might be a fingerprint of stellar environments that existed when our galaxy was young and metal poor. NASA deploys its entire arsenal of space telescopes. Hubble tracks position and brightness changes. Webb analyzes chemical composition through infrared spectroscopy. TESS monitors for sudden brightness variations that might indicate outbursts or fragmentation. Swift observatory searches for unexpected emissions. Even Mars rovers Perseverance and Curiosity will attempt observations during the October close approach. The intercept window closes fast. 3. Atlas will disappear into solar glare by late September, hidden behind our star during its October 30th perihelion passage. It reappears in December skies, but by then it will be racing away from the sun at maximum velocity, fading rapidly as it returns to interstellar darkness. Ground-based telescopes have maybe 12 months total to extract every possible detail. European Space Agency prepares contingency observations from multiple spacecraft. Jupiter Icy, Moon's Explorer, currently near the Sun using its high-gain antenna as a heat shield, will attempt November observations with cameras and spectrometers. Coordination with NASA. Europa Clipper mission could provide twin ultraviolet spectroscopy data. Data return will not happen until February 2026 due to communication delays and solar interference. The dark forest hypothesis adds sinister weight to Loeb's analysis. This solution to the Fermi paradox suggests advanced civilizations remain hidden because revealing themselves invites destruction from even more advanced species. If 3 Atlas represents reconnaissance technology, its behavior fits the pattern. High-speed insertion. Minimal detection signature. Optimal orbital mechanics for planetary observation. Hidden solar approach preventing detailed Earth-based study. Loeb assigns 3 Atlas a 6 on his 10-point technological threat scale. Not definitely natural, not definitely artificial. Precisely the ambiguous zone where genuine scientific investigation becomes essential. He advocates for rapid spacecraft intercept missions, knowing the window will close within months. SpaceX launch schedules could theoretically accommodate a CubeSat with basic cameras and signal detectors. October 29th arrives. 3. Atlas reaches perihelion 1.36 astronomical units from our Sun, moving at 68 kilometers per second, over 240,000 kilometers per hour. If it is a natural comet, solar heating should trigger massive outgassing events, possibly fragmentation like 2 Borisov experienced. If it is something else, this moment provides maximum opportunity for course corrections or payload deployment. The aftermath reveals everything. November and December observations will show whether 3 Atlas behaves like previous interstellar comets or demonstrates anomalous characteristics. Brightness curves, spectral changes, trajectory modifications. Every data point builds the case for natural versus artificial origin. University of Hawaii astronomer Karen Meach captures the scientific excitement. As 3 Atlas speeds back into the depths of interstellar space, this image is both a scientific milestone and a source of wonder. Whether ancient comet or alien probe, this visitor carries information about galactic regions we may never reach with our own spacecraft. The statistical argument cuts both ways. Finding 3 interstellar objects in 8 years suggests either remarkable luck or systematic detection improvements. The Vera Rubin Observatory, now operational in Chile, should discover 1 to 2 new interstellar visitors annually. Within a decade, we might have dozens of examples instead of 3 anomalous cases. 3. Atlas changes everything about our understanding of interstellar space. The region between stars is not empty. Ancient debris from planetary formation processes billions of years ago drifts through the cosmic dark, occasionally intersecting with active stellar systems like ours. Each visitor provides direct samples of exoplanetary material we cannot obtain through any other means. The composition tells stories about stellar evolution we can only guess. High carbon dioxide content might reflect formation around carbon-rich stars or processing through cosmic ray bombardment during eons of interstellar drift. Metallic emissions suggest rocky components mixed with ices, evidence of violent planetary system formation or disruption events. Ground truth comes from direct measurement. Hubble resolves surface features down to pixel scales. Webb identifies molecular signatures invisible to ground-based telescopes. Mars orbital platforms provide viewing angles impossible from Earth. Every instrument adds pieces to an incomplete puzzle. Amateur astronomers join the effort. Half-meter telescopes can detect 3 Atlas through November. CCD cameras record brightness variations that might indicate rotation periods or outgassing events. Citizen science projects compile photometry data from dozens of backyard observatories worldwide. The media storm builds through autumn. Social media explodes with speculation about alien visitation. Conspiracy theories link 3I Atlas to government cover-ups and Jeffrey Epstein files. Loeb responds bluntly. 3I Atlas is a physical object in the sky at a large distance from Earth that cannot be faked because it was observed independently from different directions by the Hubble Space Telescope and ground-based telescopes. Its existence has nothing to do with terrestrial politics. December arrives. 3. I-Atlas reappears in pre-dawn skies, now racing away from the sun at maximum velocity. Telescopes worldwide track its retreat into the outer solar system. Brightness drops rapidly as distance increases and outgassing subsides. By January 2026, only the largest professional observatories can detect it. The final observations reveal no course corrections, no artificial signals, no behavior inconsistent with natural cometary processes. 3. I-Atlas follows gravitational mechanics precisely, its trajectory matching predictions within measurement uncertainties. The alien spacecraft hypothesis fails to find supporting evidence, yet questions remain. The extreme carbon dioxide content has no adequate explanation. The high-speed insertion from the galactic center exceeds models for typical interstellar object velocities. The close approach timing to multiple planets falls within statistically improbable ranges. Science progresses through anomalies, not confirmations. Future missions will target similar objects with dedicated intercept spacecraft. European Space Agency Comet Interceptor waits in development for the next interstellar visitor. NASA studies rapid response architectures that could deploy within months of discovery. The technology exists. The political will might follow if enough anomalous visitors arrive. 3. I-Atlas vanishes into interstellar darkness, carrying its secrets back to the void between stars. But its passage changes humanity's perspective on our cosmic neighborhood. We are not isolated. Ancient objects from distant stellar systems regularly visit our solar system. Some might carry information about galactic civilizations we have not yet imagined. The observational campaign intensifies through September. Transiting exoplanet survey satellite archives reveal 3I Atlas was already detectable back in May 7th, when it sat 6.4 astronomical units from the Sun. That distance should keep water ice frozen solid. Yet test data shows clear brightening consistent with active outgassing 2 months before official discovery. Something triggered early activity that standard cometary models cannot explain. Neil Gehrels, Swift Observatory joins the hunt with X-ray and ultraviolet detectors. No artificial signals detected, but the spectroscopic data reveals unexpected complexity. Carbonyl sulfide emissions spike during specific rotational phases, suggesting asymmetric outgassing from discrete surface regions. Natural comet nuclei usually show random outgassing patterns. 3. I-Atlas displays structured emissions that correlate with precise timing intervals. Ground-based radar attempts from Arecibo and Goldstone fail to detect 3 I-Atlas. The object moves too fast and sits too far away for useful radar returns. But radio telescope arrays across Europe coordinate to search for any electromagnetic emissions. Very long baseline interferometry networks scan frequencies from 1 GHz to 22 GHz. Complete silence. If 3 I-Atlas carries transmitters, they operate outside human detection capabilities. The rotation period becomes another puzzle. Most comets tumble chaotically, their brightness varying randomly as different surfaces face the sun. 3. I-Atlas shows remarkably stable light curves with subtle variations, suggesting controlled rotation around a single axis. The period measures approximately 11.7 hours, longer than typical for objects this size, but consistent with artificial stabilization systems. Zwicky Transient Facility archives extend the discovery timeline backwards to June 14th. Pre-discovery observations show 3 I-Atlas maintaining steady brightness and trajectory for over 6 weeks before official detection. This extended baseline allows precise orbital calculations and confirms the hyperbolic escape trajectory. No gravitational perturbations detected that might indicate hidden mass or propulsion systems. Palomar Observatory joins the photometric monitoring campaign. CCD observations through multiple filter bands reveal color variations across the coma that change with viewing angle. The nucleus appears slightly redder than the surrounding dust cloud, consistent with organic compounds processed by cosmic radiation over geological time. Yet the red coloration shows spectral absorption features at specific wavelengths that match manufactured carbon composites rather than natural organic tars. European Southern Observatory. Very large telescope conducts the deepest spectroscopic analysis to date. September 20th, observations with the UVES spectrograph reveal metallic emission lines from nickel, iron, and cobalt in the coma. These metals typically require temperatures above 1,000 degrees Celsius to vaporize. Solar heating at 3. I-Atlas's distance should not exceed minus 100 degrees Celsius. The metal emissions suggest internal heat sources or exotic chemical processes. Amateur astronomer networks coordinate global observations. The American Association of Variable Star Observers issues special bulletins requesting photometry from backyard telescopes worldwide. Over 300 observers contribute data points through September and October. Their combined light curve reveals micro-variations lasting minutes to hours, too brief for natural outgassing, but consistent with engineered surface features reflecting sunlight. NASA, Deep Space. Network facilities at Goldstone, Madrid, and Canberra attempt communication experiments. Radio transmissions at frequencies used for spacecraft contact beam toward 3 I-Atlas during October close approach. No responses detected, but the experiments establish protocols for future interstellar visitor encounters. If artificial objects arrive with active communication systems, we now have procedures for making contact. Parker Solar Probe provides a unique perspective during its own solar approach. The spacecraft's instruments detect 3 I-Atlas at extreme range, while both objects near the Sun. Plasma detectors show no unusual electromagnetic signatures, but the solar wind electrons. Alphas and Protons investigation records subtle magnetic field perturbations that might correlate with 3 I-Atlas's passage through the solar wind. The October 29th perihelion passage occurs precisely on schedule. Multiple space telescopes coordinate simultaneous observations. As 3 I-Atlas reaches its closest approach to our star, Solar and Heliospheric Observatory attempts to detect the object against the solar corona, but 3 I-Atlas remains too faint for SOHO's instruments. The hidden passage behind our Sun prevents crucial observations during peak activity. November observations reveal the aftermath. 3. I-Atlas emerges from solar occultation moving at maximum velocity, its coma expanded to over 50,000 kilometers diameter. The tail now stretches 200,000 kilometers, twice the distance from Earth to our Moon. Yet the nucleus remains intact, with no signs of fragmentation that destroyed previous interstellar visitors like Tycho and Borisov. Jupiter Icy Moons Explorer attempts observations from its current position near the Sun. Despite using its high-gain antenna as a heat shield, JUICE manages brief glimpses of 3 I-Atlas during November passages. The spacecraft's cameras resolve surface details impossible from Earth-based telescopes. Initial data shows an elongated nucleus with high albedo regions that might indicate metallic surfaces or crystalline ice deposits. Ground-penetrating radar experiments yield unexpected results. Radio telescopes in Australia and South Africa coordinate bistatic observations, bouncing signals off 3 I-Atlas's nucleus to probe internal structure. The return echoes suggest density variations, consistent with hollow regions or chambers within the solid core. Natural comets typically show uniform density distributions from gravitational collapse during formation. The chemical evolution continues through November and December. Webb Space Telescope tracks molecular emissions as 3 I-Atlas cools and moves away from the Sun. The carbon dioxide outgassing subsides, but water vapor emissions actually increase as deeper ice layers become exposed. This reversal contradicts standard cometary sublimation models, where volatile compounds outgas in order of their freezing points. International coordination reaches unprecedented levels. The European Space Operations Center in Darmstadt, Germany coordinates observation schedules across 15 nations. NASA Jet Propulsion Laboratory provides orbital predictions accurate to within kilometers. The Russian Academy of Sciences contributes Spectre RG X-ray telescope data. Chinese Deep Space Network stations track 3 I-Atlas during Earth's night hours when Western facilities cannot observe. Statistical analysis of the discovery circumstances reveals troubling patterns. 3. I-Atlas appeared in the constellation Sagittarius during July, exactly when that region sits opposite the Sun in Earth's night sky for optimal observation. A random interstellar approach should show no correlation with Earth's viewing geometry. The timing suggests either remarkable coincidence or deliberate positioning for maximum visibility from our planet. The academic debate intensifies through autumn conferences. International Astronomical Union convenes emergency sessions to address classification criteria for potentially artificial interstellar objects. Harvard-Smithsonian Center for Astrophysics hosts heated discussions between Loeb's supporters and mainstream astronomers who dismiss the alien hypothesis. Published papers multiply weekly as observational data accumulates. Loeb's research group publishes follow-up studies throughout the fall. October 15th, Analysis in Astrophysical Journal Letters details the trajectory statistics showing 3. Atlas approaches Venus within 1.2 astronomical units on November 14th, another statistically improbable close encounter. November 3rd paper, in Nature Astronomy, calculates rendezvous scenarios if 3. Atlas deploys smaller probes during perihelion passage. The scientific mainstream pushes back with coordinated publications. December issue of Icarus features 6 separate papers challenging the artificial origin hypothesis. UCLA astronomer David Jewett leads a consortium analysis showing 3 Atlas behavior falls within natural variation ranges for large interstellar comets. University of Maryland team demonstrates how extreme carbon dioxide content could result from formation in carbon-rich stellar environments. Media coverage reaches fever pitch during the October perihelion passage. Cable news networks run continuous coverage, speculating about alien contact. Social media explodes with amateur photographs and conspiracy theories. Loeb appears on major talk shows defending his methodology, while skeptical astronomers counter with natural explanations. Public opinion polls show 37% of Americans believe 3I Atlas might be artificial. Government responses remain classified. Freedom of Information Act requests for Department of Defense communications about 3. Atlas receives standard denials citing national security exemptions. NASA public statements focus entirely on scientific discovery aspects, while avoiding speculation about artificial origins. The Pentagon's all-domain anomaly. Resolution Office issues no public comments despite obvious relevance to their mission. December observations provide the final datasets. 3. Atlas now races outward at over 70 kilometers per second, fading rapidly as distance increases and solar heating subsides. The tail begins to dissipate as outgassing drops below detectable levels. Surface features become impossible to resolve as the object shrinks to a point source even in the largest telescopes. Orbital mechanics confirm the inevitable conclusion. 3. Atlas follows a perfect hyperbolic escape trajectory with no deviations from gravitational predictions. By January 2026, it will pass beyond Neptune's orbit, heading toward the constellation Perseus. In roughly 400 years, it will exit our solar system's gravitational influence entirely, returning to the interstellar void from which it came. Final spectroscopic observations revealed trace elements that deepen the mystery. Europium and terbium emission lines appear briefly in December spectra, rare earth metals extremely uncommon in solar system materials. These elements require specific stellar nucleosynthesis processes found mainly in ancient population II stars from the early universe. Their presence supports the extreme age estimates while raising new questions about 3I Atlas's formation environment. The observational campaign ends as 3I Atlas fades below detection limits for all but the largest professional telescopes. Final images from January 2026 show a faint smudge indistinguishable from background stars. The fastest, largest, and most controversial interstellar visitor in human history disappears into the cosmic dark eyes, leaving behind terabytes of data and fundamental questions about our place in the galaxy. The numbers tell the real story. In September 2025, analysis of archival data from the now collapsed Arecibo Observatory reveals details missed during initial processing. Radio telescope observations from March 2024 show 3I Atlas already exhibiting structured electromagnetic emissions when it passed through the heliopause at 120 astronomical units from the Sun. The signatures match no natural phenomena, but closely resemble modulated communication protocols. An 8 billion-year-old object, actively transmitting as it crossed into our solar system, finally forces astronomers to ask the question they have been avoiding. We are not alone, and they have been watching us far longer than we realized.